We're still working with making slope fields for our differential equations today. What's the difference between this differential equation and the 2 or 3 that we did yesterday when we were making slope fields?
There's a y in the equation, it's not just x.
Yep, exactly. So we got a y in here rather than the last ones we did just had x's in them, right? Cosine x or root x squared minus x plus 1. This one's got x minus y. Right, so this time, rather than just being able to make like nice little columns where everything in each column had the same slope, now the y values are going to affect those slopes also. So there's a pretty good technique for doing this. And what we want to do is we just want to pick values that we want our derivative to equal. So easiest value to choose is the value for when our derivative dy dx is equal to 0. And so if we let our derivative equal 0, that tells us that x minus y equals 0, which can be solved to tell us what? Y equals
X.
X, exactly. And so that's telling us that anywhere along the line y equals x, any point that falls on that line, right, that line y equals x, the slope should be 0. So what we're going to do is along the line y equals x, we're just going to draw a bunch of lines that have a slope of 0. Good or no?
Good.
Okay. Then we'll do the same thing. So we'll pick another value. So what's the next value we want to choose?
1.
All right. Let's do dy dx equals 1. That sounds like a plan. So what does that tell us? That tells us that x minus y equals 1, or that y is equal to 1.
X minus 1.
Okay, good. So anywhere along the line y equals x minus 1, which would be approximately that line, we should have a slope of 1. So we should have a bunch of little lines with slope 1 that look like that. Does that make sense to everyone?
Yeah.
Okay. What about if dy dx equals -1? What does that give us after we write x minus y equals -1? That would tell us that y is equal to
X plus 1.
perfect. And so all of these have a slope of -1 along the line y equals x plus 1. Okay. And so we'll just continue in that same manner, picking different values for dy dx, finding the linear equation along which to put lines of that slope. So if we choose 2, that's going to give us what? Y equals x minus 2. And x minus 3 will give us 3, and x minus 4 will give us 4. So as we continue going down and to the right along this, for each of these lines, it's going to keep increasing slightly each time. So this next one should be 2. And then the next one should be a little steeper. And then a little steeper, and then a little steeper. And then going the other direction, we should end up getting lines like -2, -3, -4, and these should continue getting steeper up this way as well. Does that make sense? Any questions or issues with that? Okay. So then if we were asked to actually sketch the curve that went through a specific point, let's say we chose this point right here. The curve that goes through that, the solution curve to x minus y through that point, should have a slope of about 1 right there, and then it should flatten out and then start going up to about a slope of 1. And over here, it should get very steep fairly quickly and look something like that. Or we might pick one, let's say down here, in which case it would get a little less steep as it would eventually approach a slope of 1 up here. And down here it would become very steep. Good or no?
Good.
Anybody have any questions on how we made that slope field? All right, so anytime you have x plus or minus y, or 2x plus or minus 7y or something like that, just find the linear equations for each slope and go through them and plot them along those lines. So those pop up every once in a while. Those are a little less common than what we're going to do next, at least on the AP test. So on the AP test, it's more common for you to see something where it's either a product or it's a quotient of x and y for your differential equation. So dy dx equals x over 2y would be a good example of that. So we're going to take a look at this one now. And generally on the AP test, what they do is they'll give you a bunch of points. I'm just going to put in a few here, and they'll say something like, this is more than they'll normally give you on the AP test, but they'll say, sketch the slope field at the points indicated. And so they'll put a bunch of points on there, and you'll have to sketch what it should look like through each of those points. You won't have to do every point, I just mean you'll sketch the slope field using those points. So let's first think about what happens when dy dx is 0. If dy dx is 0, what can you tell me about x over 2y, or about x and y in general? What does x have to be?
0.
X must be 0, but what can y not be?
0.
Yeah, y cannot be 0. And so anywhere where x is 0 and y is not 0, we should have a slope of 0. So here's a place where x is 0, but y is 0, so that doesn't work. But x is 0 and y is 0. Or y is not 0, sorry. Be those ones. And what would make it undefined? If y was equal to
0.
0, but x was not equal to 0. So these values should be vertical or have undefined slopes. Good? So then from there, all we'll do is we'll just look for patterns between the different rows and columns and see what happens. So first we'll try at 1, 1 and see what we get. What's dy dx equal at 1, 1?
1/2.
Should be a half, exactly. So at 1, 1, we'll have a slope of about a half. What happens is we move out to the right from that point. The x values are getting larger, but the y values are staying the same, right? So let's say at the point 2, 1, that should be 2 over 2 or 1. So the slope should be increasing. And as we continue to go further out, it's going to keep increasing. And so we'd recognize that pattern. If we had more points to the right, we just keep increasing that slope because y stays the same, the denominator is not changing, but the numerator is getting larger. So we'll do the same thing going to the left. If we plug in -1, 1, what do we get? We get -1/2. And then if we were to continue going to the left, those x values are getting larger negatives and the y values are staying the same. So it's just going to mirror what happened on the other side. Good or no?
Good.
Okay. So then we recognize hopefully that as we go out away from the y-axis, the slopes will increase every time, but we need to figure out a starting point for each one. So at the point 1, 2, it should be a fourth. So we should start even flatter and then get a little steeper and then a little steeper. And same thing here, start off very flat, a little steeper, a little steeper. And because there's only an x in the numerator and only a y in the denominator, no x's and y's in both, this is going to end up getting mirrored down below. We could plug in the points and see. So if we plug in 1, -1, what do we get? We should get a -0.5 again. And then it should just get a little steeper and a little steeper. I don't think I did those very well. There we go. And then same thing mirrored over going to the left. Good? Same thing as we go further down. It's just going to keep getting steeper as we move away from the y-axis and less steep as we go further up and further down. Everybody good there or no?
Good.
All right. So if I asked you to sketch the solution through, let's say, this point right here, it would start off flat and it would slowly start to curve up. Or if I tried to sketch one, maybe let's say down here, it would do the same thing. If I happened to pick a point that was way over, let's see, let me get a different color for this. If I happened to pick a point like way over here, let's say this point, it would be coming up to vertical up here and extending out this way. And you'll note that I didn't curve it around because there's a rule for this that says that whenever you sketch the solution to a differential equation, always make it a function. And that's just a math rule that we've got. Whenever we're sketching that solution to the differential equation, make sure it's a function. So if I continued it up, it would no longer be a function because it wouldn't pass the vertical line test. Does that make sense?
Yeah.
All right, cool. Any questions or issues with these slope fields? It's just a matter of plugging the points into the differential equation that's given to you, and then sketching a curve if there is one that they ask you to sketch through.
So would any of these curves be like a viable answer, or would you have to draw like every single answer?
Well, so I would say something like, okay, sketch the curve that goes through the point 0, 1, so then the blue one would be your answer. The slope field is all the little red lines we drew, and then I just picked some random points to sketch curves through and say, if I picked this point 0, 1, it looked like the blue one. If I picked the point 0, -1.5, it looked like the green one. If I picked the point 3, -1, it looked like the orange one.
Okay, thank you.
Yep. So the first one we did today, x minus y, we're not going to be able to actually solve these differential equations explicitly like we did with the basic ones we were doing before. It's possible to do that, but it gets a little bit complicated, and it's more of a differential equations. Like after you finish calculus class, there's a full class on differential equations. So that's when you would learn how to do those. But these ones, where it's a product or a quotient of x and y, we will be able to learn how to solve. And those ones are specifically called separable differential equations. And we're going to do at least one of them, at least that one right now. And so a separable differential equation, like I was just saying, is just one where you have something in terms of y and something in terms of x. So a function in terms of y and a function in terms of x, either being multiplied or divided, because remember, multiplication, division, there's not really any difference, right? It's the same basic concept. And so all we have to do is separate the x's and the y's so that they can go on to the sides with the dy and the dx. And then we'll just integrate both sides separately. So in this case, we'll divide by f of y to get it with the dy, and we'll multiply by the dx to bring it to the side with the g of x. And so this is called separating the variables, and this is what we do for a separable differential equation, which is any differential equation with x and y where they're being multiplied or divided by each other. And so let's take a look at the one we just had a minute ago. We had dy dx equals x over 2y, correct? Isn't that what we just did with the slope field a minute ago?
Yeah.
Okay, so all we'll do is we'll bring the 2y to the left, giving us 2y dy, and we'll bring the dx to the right, giving us x dx. And now that we've got all the x's on one side and all the y's on the other side, we just integrate both sides. And if I integrate 2y dy, what do I get?
Y squared.
Y squared plus some constant, right? And what about if I integrate x?
X squared over 2 plus a constant.
X squared over 2 plus some other constant, right? These don't have to be the same. And so generally when we do these separable differential equations, rather than saying, all right, I got a constant on this side and a constant on this side, we'll just bring this over. And in fact, we won't even write two different constants. We'll just say y squared equals x squared over 2 plus some constant. Since we're getting constants on both sides, we can just gather them all to one side. Does that make sense to everybody?
Yeah.
Okay. And so the general solution to that differential equation would be y equals either positive or negative square root of x squared over 2 plus a constant. And obviously the positive or the negative part of it would make it not a function if you included both of those. So we'll just choose whichever one we need based on an initial condition that might be given to us. So theoretically, this equation, x squared over 2 plus a constant inside of a square root, should be what we get if we we should get that function that resembles this slope field. So suppose we put in a constant of 3, let's say, into, I didn't show you guys the slope field again, right? So x squared over 2 plus a constant should resemble one of these functions depending on what our constant happens to be. And so we're going to do that on Desmos right now, hopefully. All right, so we're going to have square root. You guys can see Desmos or no?
No, we can't.
No,
Oh, yeah, no.
now we can.
Okay, sorry about that. So you're going to have square root of x squared over 2 plus some constant. So suppose we put in a plus 3. And this is what that graph looks like. And yeah, that looks, I would argue, very, very close to what our slope field looked like when we sketched the solution curve through a point up here near 0, 1. True? Those are pretty darn similar, right? I know that's not through 0, 1, but we get the idea that the slope field should resemble the graph when we actually solve the differential equation.
Yeah.
Cool. So any questions or issues with that? All right, we are going to stop there. We don't have time to do any more. So we're going to finish covering this stuff on Tuesday, and then we'll have a quiz on Wednesday. Quiz on Wednesday will cover, let's see, what will a quiz on Wednesday cover? It will cover the motion type problems, which I'll put some up for you to work on over the weekend, and also some of the basic differential equation stuff that we've been doing.